With my mobile internet.
Just click on the garden. Okay, so welcome back, everyone. So the next speaker is Niels Reimers. So it's my pleasure to introduce him. So Niels was a PhD student and then a postdoc at the UTP lab in Darmstadt. Well, from there he moved to Hugging Face, where he was leading a group on neural search. Well, more recently, or very recently, he moved to another startup in Canada, Cohere, where he's also working on neural search and other types of natural language processing problems. So, well, the next lecture is going to focus also on neural information retrieval, now with the focus on dense retrieval models, dual encoders, where both queries and documents are represented as dense vectors. Okay, so let's welcome Niels.
Okay, yeah. Thanks so much for the intro. So, as mentioned, I'm a PhD and postdoc at the UTP lab in Germany. So I was the very first PhD student in Germany in the lab to look at. So the computer vision people were all starting to talk about deep learning. You have to know deep learning were kind of really uncool in the 2000s. So I remember like one IBM guy had an interview with Jeffrey Hinton in Toronto, and then Jeffrey Hinton started to talk in, I don't know, in the early 2000s neural network. And then this IBM guy said, "Oh, please stop talking about neural networks. I don't care. We're using support vector machines and feature engineering. That's a lot cooler." And he said, "Okay, if Hinton will continue to talk anymore on neural networks, I will leave the room. But it's like a really boring, uncool topic from the 90s and 80s. We don't do this anymore in 2000. And then in 2010, 2011, 2012, computer vision started to look into neural networks. And then in 2012, 13, also NLP looked into neural networks and deep learning. Yeah, luckily it turned out to be really relevant, and also transformers most recently turned out really relevant. And yeah, probably some people know me from sentence BERT or sentence transformers. I looked into how can you use transformers to learn embeddings. This came mainly out of frustration. So at that time, Google had universal sentiment enclosure and Facebook had the InfraSend, but they just published the model and not the training code. So I said, okay, screw them. I want to learn how to learn embeddings by yourself, read a library. There's a lot of educational material, how to learn your own dense embedding representation models. Last year, I joined Hugging Face to be a team lead and build up the neural search science team. Some output from there is the BEER benchmark, where we tested, where we focused a lot on out-of-domain performance. We'll also give a bit more information on this, on out-of-domain performance of neural search models, also what Andrew talked about, like doc25 query, cross encoders, and so on, how they perform well there. And also from my research group, TSDE and GTL, are two new recent publications. Sadly, we don't have a fancy symbol yet for these, so we should probably come up with some symbols for them to make them sticky. And then 2 weeks ago, I joined Cohere. So Cohere is a startup from Toronto, from the Hinton group. And we're using very large language models, like up to like hundreds of billions of parameters. That will be doing research. How can you use them to enrich search? So how can you solve search if you have like very large language models to have? So today I want to focus on sentence embedding models or text embedding. So sentence embeddings is a bit misleading because it can be any text longer than a sentence, or not too long because there are transformers, not scale from really long text. But in general, you start with like some input text. What Andrew already presented, you map it to the token embeddings, and then you get the contextualized word embeddings from BERT or another transformer network as an output. And what we want is some fixed length embeddings. So we do some pooling where you can either take a CLS token or you do some average of these contextualized word embeddings. And what it gives you is it's a vector space. So probably still some know it from introduction to linear algebra. You have a vector space here in a 2D case. And in a vector space, you can do really efficient operations. The most interesting operation I find is search. So you encode all your documents in the vector space, and then some query comes, you do the same encoding process, you also encode it in the vector space, and then you just check in the vector space what's the nearest neighbor. And these are documents hopefully relevant for the query. So that's the goal. You encode document and query, and a relevant document should be close to the query in the vector space. In terms of implementation, it's kind of easy. So you encode your query, you encode your document, you do your transformer network, you do your pooling, and then you have like some fixed size vector, and then you have some similarity function and cosine similarity or Euclidean distance or dot product, and then you find the closest neighbors. So in theory, the architecture is not so challenging, but there are many small details which are interesting, especially if you want to push forward to a state of the art. How do you train these models to be like really good model? So these dense embedded models, they can solve some nice things, some gaps in information retrieval, which are quite problematic for lexical search models. One is the lexical gap. If you have like ESSIR2022, then US, USA, and United States, they are all different tokens. So if you search for USA, you will not find any documents talking about US or United States. It can respect the word order. So if you search for how to get a ESSIR coming from Germany to Canada, or the opposite, like come from Canada to Germany, or a lexical retrieval model like ESSIR2022, that's the same. So it's exactly the same query. You get exactly the same search result, but a user has a different intent for these two queries and want to see different results. And also it knows about related terms. So maybe you want to compute the Spearman correlation in NumPy, but there is no Spearman correlation in NumPy, but there's a Spearman correlation function in SciPy. And the retrieval model knows NumPy and SciPy, that's really similar. So these are libraries you can often use interchangeably. So it spits out the results and say, here are the results, how you can compute Spearman correlation in SciPy, even such that you did a search. What's also really cool is multilingual and multimodal search. So everything is connected to a vector space. In multimodal search, you have some text, the cat on a table, 2 dogs on the snow, London tonight. And then you encode images in the same shared vector space. And then you can just do search. So you search for 2 dogs in the snow. You find this dog image is the closest in the vector space. And you say, okay, you have been searching for this, and this is the closest image I have in my database, and then you can return this. So same operation, doesn't matter if you search for text documents or for images, audio, video, whatever, everything is just a vector. And also the language doesn't matter. So you can type in this question in any language, and then it will be projected really similar, really close in a vector space, and then you can just check out what's the closest image. And now you have like an image search function working on hundreds of languages. You do not need to describe anything. What you see in the image just works, and you can search in whatever your favorite language is. If you have any questions in between, just feel free to raise your hands. I think plenty of time. Great. So now I want to talk a bit more on how do you train these representation models. One loss function, which is really, really good, which I recommend. It has a lot of different names, so it's really hard to stick to a name. So in theory, I think the oldest reference is from 2003, list ranked loss. But then people did this with in-batch negatives, and they call it different names. Sometimes you find it with info-NC or anti-cross entropy loss. I call it multiple negative ranking loss. So when you read it in different papers, people call it different names, which makes it a bit hard to see, okay, it's always the same loss. but that's a lot of the models used for bioencoders until last year. And then there was a switch to go to margin and MSD loss, which I don't know if I will cover it today, but yeah, so this was like state of the art until last year. And so what you do is you have pairs. So pairs can be anything. It can be a query, it can be an answer, it can be a question, it can be some duplicate question from an online community, can be a paper title, and can be the cited paper title. So the word paper cites attention is all you need. Can be an image and image description. It can be, I don't know, some audio and some video. So just some pair where you say, okay, these two are connected and you want them to be close in the vector space. So you want all these pairs to be close in the vector space. At the same time, if you have a mismatch between I and J, they should be distant in the vector space. So what you encode A, which is the anchor, and P, which are the positives in the vector space, and A1 and P1 should be close. And all the others, A1, P2 to P5 should be distant in the vector space. And then you learn the model, or you teach the model to represent it in this way. So the mathematical definition looks like this. I will not go too much into the math here. It's kind of, or I will present like a more simpler version of this. But what you do is you check what's the similarity of the positive versus the similarity of all the others. And similarity function can be different options. Most common is either to use cosine similarity or dot product. So here comes the intuitive explanation. So it's kind of like a multiple choice test. So you have like from school, you know, you have a question, how many people live in Berlin? And then there are 3 different options, around 3.5 million people live in Berlin. And then Washington DC is the capital of the US, and the 21 Olympics are held in Japan. And you ask the model, okay, which of these 3 answers is the correct answer to the question? So what you do is you compute the embedding, the representation, you compute the similarity between the anchor, in this case the question, and the positive, in this case possible answers. And then you say, okay, the model predicts for A1, P1, 0.5, for P2, 0.3, and for the last one, 0.1. And so this is the prediction, and you know, okay, A1, P1 and A1, that's the correct pair. So this is the gold label. So this is just cross entropy loss. So you have like, in this case, 3 different options. So you compute the score for 3 different answers. You say the first one is correct, and then you do cross entropy loss on that. That's the question.
So last paper, you're looking at a classification. You're doing a classification task with a single the ranking task where you might have binary preferences or other aspects or rank faults. Have you considered other losses in that step or help with that?
Yeah, so the question was like different losses, preference losses, and so on. I think the challenge is like what type of data do you have at hand at scale? And often you have like some binary data at hand, like for example, you can mine Stack Exchange. This gives you like 50 million question answer pairs. And here you just know, okay, this is the question, this is the answer. Or you mine Reddit where you get a title and body and you get like 200 million question body, like short form of the question, long form of the question. Or you mine semantic search and you get 200 million scientific titles, scientific extracts. So this is what you can get at scale. More fine-grained where you can say, okay, this is preferred over the other. It's a lot harder to get at scale if you're not Google or Bing. You have like a large user base with quick logs, and you can say, okay, what are like different preferences of users. So you do it in a batch. So you don't do only like 1 question and 3 answers, but if you train these models, you do it in a batch. So in a batch, you have like 3 question answer pairs. How many people live in Berlin? What's the capital of the US? Where are the Olympics this year? And then you have these different answers to it. So for every question, for every answer, you encode individually the embedding, the representation, can be dense, can be sparse, doesn't matter. And then you compute the matrix, like the matrix of all the similarity functions. So what's the similarity between A1 and P1 and so on. So for all 9 combinations, you compute the similarity based on the similarity function. And then you say, okay, your classification task, you say for the first question, the first answer is correct. For the second question, second answer is correct. And the third one, the third answer is correct. So that's just classification with cross entropy loss. Just a bit different how you compute the lodges, which you feed into your cross entropy loss. You can also implement this quite easily in PyTorch. So it's no big magic you need to do. You have your embeddings for the anchors. You have the embeddings for the positives. You compute your similarity function, which you might scale with some factor. I will talk about this in a minute. Then you have the labels where you just say, okay, the answer to the first question is the first, well, for the first question, the first answer is correct. For the second answer is correct, and so on. And then you just call cross entropy loss between the scores of the labels. So it's like 3 lines of code to compute this loss. The magic is not in the loss, but how you create the batches, where we'll talk more in a minute, because that's really relevant how you create the batches. And this makes a difference how good your model is. Question.
Is there any option to make in NLP like in an unsupervised manner? Like, for example, in computer vision for contrastive learning, they have all these rotation, flips, and stuff like this.
Yeah.
I know that there is SimC, which they put the same, but
yeah,
is there any better?
SimC doesn't make sense. I will talk on this a bit later. So it doesn't work. And also you have to be careful. You read a lot of papers on this claiming good results, but they do not really work due to flaws in the benchmarks. It's really hard to make it work completely unsupervised, where we have been also working a lot on this. Also in computer vision, it's a bit easier. So you rotate an image, I don't know, I have a cat image, I rotate it or I flip it, it's still a cat image. If I take a text and I change a word like, I don't know, do you like this one? And I change the word love to hate, do you hate this one? It's like really different text. So it's a lot harder to do this for text. And so far, I've not found any good solution how you can train a good representation model completely unsupervised. There are some ways how you can pre-train, and then you take some pair data to fine-tune it, but no really good solution where you can completely train unsupervised and give like any model that matches performance of supervised models that are trained with supervised label pairs. So how do you compute the similarity? So A and B are vectors, stands for sparse vectors. There are different options how you can compute it. One is the dot product. The other is cosine similarity. What's a bit more common, instead of cosine similarity, is scaled cosine similarity. So you take the cosine similarity and you scale it by some value. And of course, you can also do scaled dot product, which is a bit less common, I would say. So either you use dot product or you use scaled cosine similarity, which also has a big impact on the vector space it learns, which I will also talk about more. So with cosine similarity, the highest, or the vector which has the highest similarity is the vector itself. So I asked a question like, how many people live in this farm? The best answer to it is like, how many people live in this farm? So exact same text has the highest similarity. For dot product, it's different. So the dot product of A and A can be lower than A and B. So if I ask the question, how many people live in this farm? Another text can have a higher dot product and be more relevant to this question than the question itself. So this has a huge impact on the vector space, how the vector space looks like, and also when you use this model for search, which types of results you get in return. With cosine similarity, you have normalized vectors. So when you normalize the vector, so every vector has length 1, then cosine similarity is identical to dot product. And also, if the vectors are normalized, it's proportional to Euclidean distance. So if you work with a vector space where all the vectors are normalized, have length 1, and cosine similarity and dot product and Euclidean distance is all the same. So which makes nice these models to work with k-means clustering. With dot product, you don't have these properties. It can also be a bit slower with certain approximate nearest neighbor methods because they want to know what's the max length of a vector, and this is not known. And also it does not work well with k-means clustering because of these strange properties that something can have a higher similarity than the item itself. And we tested to train models with cosine similarity and tested to train them with dot product. So same procedure, you just swap the similarity function. And the results you get is quite different. So we tested it, for example, on the track COVID data set. So that's a retrieval data set on COVID-19 scientific publications. And on the x-axis, you see the number of tokens the best result has. So the number one result, which how many tokens does it have? And here you see a frequency distribution. And with cosine similarity, you retrieve a lot of short documents. So in that document collection, you have some scientific papers where you just have the title, and some scientific papers where you have the title and the abstract. And the model was trained with cosine similarity, likes to retrieve results where you just have the title, which are really close, because that's really close to the question or the query you type in. And as mentioned, the highest similarity to a query with cosine similarity is the same query. With dot product, what you see is you retrieve a lot longer documents. So it likes documents where you have query and where you have the title and the abstract. So this makes a big difference for the user experience. So with the blue one, you get like short answers like, okay, here I just have a title. And with the orange one, with the dot product, you get like, hey, here I have a title and an abstract. These are longer text I retrieve for you. What you prefer depends on the user. So for track COVID, there was like a really strong preference from annotators to also get the abstract. But for other cases, sometimes you like more shorter text because you do not like to read. For other cases, you say I like longer text because it has potentially more information. So it's really hard to decide which similarity function you should use. So if you just train with cosine similarity, cross entropy loss does not work really well because the similarities are really, like the difference are too small. Like you have some documents which have like, I don't know, 0.9 similarity, the other document has 0.5 similarity. And that's like too small, too close for cosine similarity to be considered as relevant. So people just scale it. So they take some factor and multiply cosine similarity by this. And this is kind of a black art so far, like which value do you choose? Common values are between like 14 and 20. And the convert paper, they started at 1 and then they increase it up to 23. The clip paper said, okay, we have no idea what's the right scaling, so we just put it as a parameter and let the model learn this. And it's really unclear, does it make an impact or not? Does it depend on data, on the task, and the model you use? So this, as mentioned, just black art, how you select this, the scaling factor. There's also symmetric multiple negative ranking loss. So where you compute the loss between the anchor and the positive, and you at the same time you flip it, and you say you compute the loss between the positive and the anchor. So you not only want to have like the text close to the images, but you have also this image and you want to find what's the right text describing this image. So it's like multiple choice, but in both ways. So not question answer, but also you have the answer and then what are the possible questions to it. It's also unclear what's the impact of that. So a lot of black art and magic in it. The LABSE paper from Google, they said, okay, we add a margin to it. So we're not only wanting to have the right answer be really close to the question, but we want that the model is really, really confident. So they add like a margin. So the original embedding space, you have these three classes, they're kind of close. And what they do is they add a margin. So they penalize when two clusters are close in the vector space and say, okay, we want some distance to it so that we have some error rule. For this specific model, so it's a multilingual model where they want to find like translated sentences, it works quite well. For other types of tasks, it does not work that well. So again, how you choose the loss function has a big impact. How does the vector space look like? And where will it be good and where will it not be good? Okay, that's so much on the loss function. So this was like the most mathematical part on this talk. Any questions on loss function?
So what if this scaling for the cosine similarity, would it make any sense, or something like instead of scaling the whole cosine similarity, just scale one dimension within the like, two vectors to like emphasize the influence of the single dimension?
Yeah, this cosine similarity will normalize the vector. So it will normalize it back to like unit length and then compute the dot product. So if you just scale one dimension in the vector, it will give like a lot of weight to this vector, but it will not change the cosine similarity. It will be like just between -1 and 1. And this doesn't work with cross entropy because the scores are too close. So cross entropy requires some scores between, I don't know, -10 up to 10, +10. So you want to scale it up to be within this range.
Maybe confusion of doing that, because you show that the similarity will be good for short text, the other one for longer.
Yeah.
We just combine them.
Potentially. I mean, that's totally the challenge if you create a model and you want to have it universal useful. Like you don't know how will people use the embedding model. Will they use it for retrieval? If they use it for retrieval, I think dot product is better. But if they use it for clustering, then cosine similarity is better. If they use it for duplicate detection and deduplication, also cosine similarity is better. So you have to make some trade-offs and say, okay, what's the target for my model? And if you don't know what's the target because you put it out as kind of like a foundation model, the users can use it, you have to find like the right balance, or you have to offer like different options. Great question. Okay, so the loss function is one relevant part. The other relevant part is how does the batch look like? So typically, if you fine-tune a transformer network for classification, you do not care about batching. Also, if you do pre-training with math language modeling, you do not really care about batching. You just batch, you distribute it across your accelerators, GPUs, whatever, and yeah, it just works. I found for learning representation models, the batching plays an extremely critical role. So I pushed my team to learn really well how do you write data loader in PyTorch, because that's where we spend most of our time, like data loading. Because it's the most simple way how you can improve your performance. So this is like a really nice plot from the Rocket QA paper. Here they have the batch size. Here they have the performance. And here we have just pairs. And as you see, as you increase the batch from 128 to like 8K, the performance increases. So it's really simple, just make the batch larger. It becomes difficult because at some point you run out of GPU memory. So if you have like a V100 32 gigabyte GPU, you can fit in batch like 100. So if you go to up to like batch size 8K, you have to distribute this across GPUs, across servers, maybe across data center rooms, and then it becomes like really challenging to train this in a distributed way. But in theory, it's the most simple way to improve the performance, just increase the batch size. In every case, I saw it when you increase the batch size, the model gets better. So really simple and easy way. Another trick which requires more thinking is using hard negatives. So this is the red line. So as you see, when you have a batch size of 128 and you go from pairs to triplets with a hard negative, which I will introduce in a minute. Also, you make a big performance gap improvement. And if you combine both, so you train with hard negative on large batches, that gives you the best model. So hard negatives, you go from pairs to triplets. So before you have like an anchor and a positive, and then the n, now you call a hard negative. And the vector space looks a bit more crowded. So you have your anchor, you want this P1 to be close in the vector space, and all the other P's and all the other N's should be distant in the vector space. And the N, we call it hard negative, it should be really close to the positive, but it should be like not the correct answer to it. So like in the previous example, I said like how many people live in Berlin, and there was like only one answer. Berlin has a population of 3 million people. So this was like really easy. If you imagine this in a multiple choice test in the exam, that's easy. You do not need to know anything about Berlin. Just say, okay, 3 million, or this is the only answer with Berlin in it. I cross it as correct answer. So this hard negative is more like, okay, you have some answers which are really hard. So you have like how many people live in Berlin, and the first answer is like around 3 million people live in Berlin. The second answer is around, I don't know, 10 million people live in Berlin. And then you need to know, okay, how many people live in Berlin to know, okay, what is the correct answer to it. And there are ways how there are good examples for hard negatives and bad examples for hard negatives. So bad example would be how many people live in London. So correct answer, 9 million people live in London. Bad hard negative would be London has a population of 9 million people. So just think about exam. Both answers are correct. And if a student takes this as an answer and gets like the minus for it, he will start to complain and say, hey, professor, it doesn't make sense. This answer is also correct. So what would be better is like an answer like this, around 1 million people live in Birmingham, second to London. So it also talks about how many people live in a city in UK. It also mentions London. So that's a lot harder to pick. For a human, it's easy, but for a model, it's a lot harder to pick. So what you want to find is hard negatives that are so hard, or which are really, really hard, but they're not correct yet. And this is like really, really hard to create it at scale, to find answers which are really close to the correct answer, but which are not correct. So there are two ways how you can create these hard negatives. One is to use some structure in your data. For example, you say, okay, I have the title, and then my title, the bird paper, cites another title like attention is all you need. And attention is all you need cites another paper, I don't know, from some other field. And you assume, okay, bird and attention is all you need should be closer than bird and the other paper, which is cited by attention is all you need. So you exploit some structure you have in the data to create the triplets. Or in QA, you can do like a question, and then you have some answer with a lot of stars. So on Stack Exchange, this is the expected answer. That's really good. And then you take an answer which is like really bad, has few stars or no stars or negative stars on Stack Exchange, and you create like a triplet like this. Strategy 2 is to mine hard negatives. So if you don't have the structure, you look into your data, you find with BM25 the top 100 most similar text to the anchor or the positive, and then you go from the pair to the triplet structure and train with the triplets. You can also improve the quality with better batches. So for example, on Stack Exchange, you have like a lot of subforums. So there's Stack Overflow, but also traveling and cooking. And what you could do is just get like the 50 million questions from Stack Exchange, randomly pick your examples. And then one batch would be like a question about Python with the respective answer, a question about traveling, a question about Pastor. And here it's like really easy for the model to find the right answer. So it just needs, okay, there's a question about the Python. So from the multiple choice test, I just take that one question which talks about programming, and this will be relevant. And if you do the sampling randomly, that's in the most case the correct answer. So a better way would be you just sample pairs from a subforum. So for example, from Stack Overflow. So now you have a question about Python, Java, and C in the same batch. So the model at least learns to differentiate between different programming language and paradigms and frameworks, but still it can just look, okay, this is a question about Python, and here's like one answer talking about Python. So this must be the right answer. And so the even better approach would be to do it on text. So you have a question about Python, a question about pandas, and a question about NumPy. And then the model really needs to understand what is the correct answer to it. So there's like no way of cheating or like easy bypass to find the correct answer. Adding random batches might still be needed. So if you just have like these really hard batches, it can happen that vector spaces overlap so that your programming question from Stack Overflow overlaps with the travel questions, because it never has, or the model was never asked to differentiate a programming question from a traveling question. And then you get like really funny results in at inference. So you take your model, it was trained really well. You have like a really simple question like how do I create a list in Python, and it returns you like some travel answers or cooking answers. So it can make sense to mix it in, like to have some nice blend where you say, okay, this is more difficult batch where all the entries are really similar, and you have some easy random batches. Any questions on batching strategy? So yeah, as mentioned, so loss function is relevant if you train representation models and how you do the batches. Like really think about how do you create like nice large batches with good properties so that the model can learn a lot from it.
Let's say I'm building like.
Okay.
Okay, I was just want to ask if you have, assuming you have no good strategy to have hard actives, is it still beneficial to just take random samples?
Yeah, I mean, you can take random samples from direction. So this gives you like the black line, but trying to go to mine find negatives, so you take EM25 to find passages which are relevant, or according to EM25 gives you like a mine hard negative, but there you need to be sure that it's not relevant. So maybe EM25 works really amazing well, and gives you like a passage which is also a nice answer to the question. And then you have like this issue like of this bad example where the positive and the negative are both relevant, and the student and you as professor would consider them those as correct answer to your question. And this usually confuses the model, and I don't know, it's like students. So if you get a negative point for this multiple choice test, it really confuses them, right? If they get like a negative point. And same with like models, they get totally confused.
I see. So essentially the idea is that it's important that you push basically these points in the vector space apart that you otherwise close together. The negatives.
Yeah, so here we would push, for this as an example, how many people live in London, and we would push around 9 million people live in London close, like A1 and P1 should be close in the vector space. But with the bad example, London has a population of 9 million people. It would be pushed far away in the vector space. Model would be punished if it's close in the vector space. This really confuses the model and tries to find, okay, why do we consider A and P close, but A and N close? Is it based on text length, phrasing, syntax? That's not on semantics.
Well, essentially, there's like no benefit to pushing a point further away that's already far away.
Yeah, but this is already in the loss function. So you have the cross entropy loss. If the similarity is small, the loss is also small. Yeah.
Question of this mathematics, because sometimes it may be really expensive to collect them. But that still makes sense to increase the training data. This hard mathematics that we manage to collect and also some random just increase the size of training data. Or it's not the way you
so you have automatically these in-batch negatives. So you have your batch, and so you've already used the examples from the other pairs or triplets as negatives. So you already have like random negatives. But I find it always beneficial to add for every pair like one hard negative. So to use some way like EM25, like also more sophisticated ways how to find hard negatives. And then you also do some denoising. So you check is the hard negative actually a negative or not, where the crossing coder plays a role. So you ask the crossing coder to check, okay, is this negative really a negative or not? And then the crossing coder says, yeah, it looks like negative, so it's a wrong answer to the question. So we use that, or the crossing coder says, no, it's too similar to the question, or it's also answered the question, so you should not use that. And so what we see is like a big interleaving of different rule search approaches, like crossing coder, as Andrew said, it's really good, but it's horrible slow. But it's really good to denoise your data and gives you like nicer, cleaner data. And if you train a model with nicer, cleaner data, like a bioencoder model or representation model, gives you better performance. Yes.
example, there's all index in the training data set, and expect they could be called the groups of index that has the same domains.
Yeah.
There's anything else.
Okay, so if I understand correctly, like how do you create like hard batches like this where you say, okay, it's like different properties. I mainly did it with pre-processing. So you think about like how can I put my files into different, how can I organize my data in different files? Another challenge if you train on really large data sets, so typically if you do like, I don't know, Kaggle style classification training, whatever, or university lecture style classification training, you load your SST2 data set into RAM. So these are 6,000 examples. So this is like 10 kilobytes of data or 100 kilobytes of data. So it's easy to load it in RAM. But if you train on really large data sets, so for our embedding models, we use like multiple terabytes of data, and you don't want to load like multiple terabytes of data into RAM and then to stream it to the training procedure. So you think about like how can you put it on disk so that you can streaming. So you read from disk, you tokenize it, you pass it to your GPU, TPU, and then you do your gradient update. So it's a lot of thinking how to organize the data, how do you do shuffling, because if you stream from this, you cannot do shuffling, you cannot shuffle your data between epochs. So there's like a lot of code and tricks involved, how to organize the data, how to shuffle data. Some data sets are small, so you can load them into memory and shuffle them. If you have a large data set of Reddit of multiple terabytes, you don't want to load it and shuffle, so you shuffle it one time on disk, and then you just read the shuffled data from disk. So a lot of work is done on data pre-processing and organizing, and then you just stream it to the training. Yes.
In the breakthrough performance and the number of database, why the performance graph when the number of datasets to
Yeah, that's a good question. That's also what the authors asked in the Rocketeer 8 paper. So why is it good to train with 8K, but bad with a batch size of 16K? I could imagine that if the batch size is too large, you get randomly another correct answer in it. So if you have a multiple choice question, you have a question and then you have one correct answer, and then you add like 16K other possible answers. There's some probability that this one out of these 16K random answers are also relevant. And this, as mentioned, confuses a student in a test, it confuses the model if there's another alternative answer with what we would consider as relevant. So, but with 8K, the probability is still small enough that you don't have to care about it or that it does not affect the model. And at some point, it will affect the model because you have some alternative answer, which would be also positive, but the model, we have forced the model to say this is a negative.
Can you apply this same setting to output retrieval? Because for question answering makes sense because you are looking for maybe only one relevant document, but in output retrieval, you're looking for a set of relevant documents. Maybe picking those hard negatives. If you don't want labels for all of them, maybe you're picking some of the relevant documents.
Yeah, so hard negatives, they push the performance, but it can be really challenging to get them, especially also if you have like a lot of redundancy in your data. So if you have like some query, I don't know, who founded Facebook, and in your corpus you have like hundreds of thousands of relevant documents. It's kind of hard to find like the hard negative here. So that's why I find it quite helpful to take a more powerful model, like a cross-encoder model, to rule out all the bad examples, to find you, okay, this is really probably the best hard negative to use. And there you can use like a really large and slow model because you just need to do it once. And once you have like a good hard negative, you can use it to train the more efficient bioencoders. Right? So now I come to more limitations of dense embedding models. So big limitation I find are unknown words, call them curse of the unknowns. So how do bioencoders handle unknown words, which can mean either use pre-training, so the BERT network has never seen, I don't know, some certain words which has been trained or published after BERT, like I don't know, Big BERT Pegasus, or also it has not seen it during fine-tuning. And the issue is that our language constantly evolves, especially, I don't know, we propose new architectures with new fancy names, new startups are created. And then how do we put these words in a vector space like XLNet, which is a transformer network, Klex chain, which is like some blockchain cryptocurrency, Forward is not a spelling mistake, but a startup from Israel. And this XOZ, whatever error code is connected to Microsoft issues with the activation key. So if the model has never seen such a word, such a combination, where do you put this in a vector space? For us humans, it's also impossible. If you do not know what this means and you have never seen it, you do not know it's connected to Windows not being able to authenticate your license key. And also, how does it learn new synonyms? How does it know that coronavirus, COVID-19, and SARS-CoV-2 is connected? So just from the words, kind of hard to know this. Also, to make transfer from like question to like acronyms, like which vision transformer model is the best, to know that which stands for vision transformer. It's kind of hard to make this connection if you have never seen this. And for dense model, this is like kind of big issue. So you take a word like Big BERT Pegasus. So this is some long form transformer network, I think on images or so. You put it into a dense encoder and you force it to like some low dimensional dense vector space. And it needs to pick the right corner in it just from the word itself. So it has never seen the word. And sadly, it's not doing a really good job. So the most similar words are big boss, big data, and big ass. So it thinks this architecture is close to big ass. And if someone writes about like my big ass, big data application, it will be ranked really high, but it will not be ranked to like transformers and BERT and Roberta and attention is all you need. Here, the sparse representations we just saw in the previous lectures do a much better job. So it does not try to force it to a dense vector space and try to find the right point, the right corner in the vector space. So it just does a word piece tokenization on it and just say, okay, I don't know what the word means, but I know that the individual word pieces are kind of relevant. So it assigns like a relevance force for Big BERT Pegasus and just checks for documents that have Big BERT Pegasus in it. And also tries to identify some related terms. So BERT and BERTs, that's kind of related. So maybe I look also for documents that have Big BERT Pegasus in the text, and also big and giant, that's also often kind of related. So if someone search for like giant BERT Pegasus, they will find Big BERT Pegasus. So I think these sparse representation models like SPLATE, they do a much better job of unknown documents. And that's why we see them also perform a lot better if you try to go to another data domain, because they don't try to infer meaning. They say, oh, I have no idea what this word means, so it just falls back to a lexical matching. So last year, I think, yeah, last year we started, well, I was kind of puzzled. So we have these neural search approaches on MS Marco, and everyone was pushing for and say, great, new state-of-the-art results. We get better and better, so much better than BM25. And then you take these models and you apply it to your really specific domains on, I don't know, medical information retrieval. And you see it works really badly. It works worse than BM25. But everyone is so excited. And as we saw in the previous lecture, it looks so much better on MS Marco. So why does it work so badly for, in particular, like medical applications or legal documents for programming questions? So what we created last year is we wanted to focus more on this out-of-domain retrieval. So you train on one data set, MS Marco, and see how does it perform a lot of retrieval tasks. There we created BEER. So MS Marco is mostly you have questions, short question, and then you retrieve a longer document. But information retrieval is a lot more or a lot richer than just question to the answer. So for example, in tweet retrieval, we have some news article, so that can be quite long, and we want to find tweets talking about this news event. So we have like a kind of long query, and we have like short documents we want to retrieve. Or on argument retrieval, we have some controversial topic, and we want to find pro and con arguments on that. So we collect a lot of data sets on different tasks and different domains, and we tested different models on it. So first we tested the bioencoders, and what we saw, the dense bioencoders, they work really well. So this is MDCT10, so that's a different metric. But we saw in domain on MS Marco from compared to EM25, we get like an 18-point improvement. So amazing. So the statements are true. But then out of domain on bioAsk, so these are biomedical applications, we see it's a lot worse than EM25 on SciDocs, which is also on scientific application. It's also worse on EM25. And actually EM25 was better on 10 out of 18 data sets compared to the dense embedding model. So in most cases, use at that time, use EM25. Now everything changed, but at that time, use EM25. It was better than the neural search approaches. And we tested a lot of different approaches to see how well they perform. So we had the BM25 and cross encoder and they introduced in the previous lecture, and also DocT5 query, and also introduced in the previous lecture. CoBERT is a multi-vector dense approach. TASB is a single dense approach. GenQ does query generation to encode a bioencoder. ANSI is a dense approach. Sparta is a learned sparse representation, so it's the previous version of SPLATE. DPR is from Facebook, it only works well on Wikipedia, and on all other data sets it works badly. And DeepCT also only works well on SmartBook, but on all other data sets it works badly. So the output was lexical search is still a really strong baseline. If you add a cross encoder to it, can improve your performance in nearly all cases, except for 2 data sets, which are really special. And dense embedding models, they have like issues for unknown domains. And sparse embedding models, SPLATE 2, sadly it's not here. It's better for known, it works better for unknown domains. So cross-encoder and bioencoders, you can also check how data efficient they are. So here we have like a small experiment where we check how many training samples we have and what's the performance. So this is on semantic textual similarity. And we see that cross-encoders work much better, but they are also more data efficient. So if you go with the bioencoder to low data regime, like 500 training examples, they perform quite badly, while the cross-encoder can still get a quite good result, even if you have little data. And if you compare these results, you see in domain performance between dense models and BM25 plus cross-encoder, not so much of difference, but out of domain, like bioAsk, you see quite a difference between BM25 and then the dense model performs quite badly here, but the BM25 plus cross-encoder works really well. So you see cross-encoder can generalize nicely to new domains, unknown domains, while dense models cannot do this. And now recently SPLATE also showed it can generalize nicely to new domains. Any questions on that? Yes.
Is there any reason those sparse embedding encoders better for unknown domains called encoders is poor at?
Yeah, so as mentioned, dense embedding models, they have the issue of unknown words. So you go in the biomedical domain, sees word for first time, doesn't know what to do. So you see the word XLNet, for example, in Transformers XLNet, it does not know what to do. It tries to infer the meaning in the dense vector space. And most often this meaning is really, really bad. The sparse approaches like SPLATE, they don't try to do this. They just say, okay, I have no idea what this word XLNet means, so I just keep it as it is. So it does fall back to lexical max. So if someone searches for XLNet, it will find documents on XLNet. While if you do this with a dense model, you type in something and then you find really unrelated terms. Yes.
definition of sparse retrieval. So is the reason for using this sparse retrieval as well, like having the animal first, or there's some different reason for using this?
Yeah, good question. Yes, so what's common now is to use hybrid search, where you use EM25, maybe at some point split and combine it with dense embeddings. The reason is also these unknown words. Also, if you search for a specific term, like, I don't know, some error code, I mean, it's really hard to beat lexical search on this. So if you search for some hexadecimal string, this is your error code, error message you get from Windows. I mean, you just can scan for documents which have this error code in it, and it will be quite likely relevant. And that's where BM25 is extremely strong on, find documents where you have an exact match. Dense models are more good in the fuzzy domain, like, I don't know, like more, where it's unclear, where you do not look specifically for the words, like what's the capital of the US. And if you combine those, you can get the best of both worlds. So you get the fuzziness from dense embedding models, and you get the lexical matching power from the M25. But at production, in theory and academia, it's nice to deploy these. In production, it's kind of challenging, because so far there are no good solutions for hybrid indices. And so you have to maintain like a sparse BM25 index and some dense index. And this gives you like a lot of headaches. So how can you ensure that they're in sync, and that you don't have like different data and the different indexes? And the larger your operations, the more difficult it gets. Again, it's a good, I think it would be a good startup idea to start like some vector database and hybrid search. I see a lot of potential there. Great. So why do we care about bioencoders and representations and do not use cross encoders or double query? The answer is speed. So cross encoder is roughly 60,000 times more expensive at inference. So if you have like a lot of budget and you don't care about cost, if you run a company, then you can use a cross encoder and get really good results. But in most cases, search has to be really cheap. Like, I don't know, you're on Amazon, the first thing you do is you hit the search bar, and they do not want to spend like many dollars to get the results, but they want to spend like pennies or slices of pennies to get the results to you. And their bioencoders or representations are a lot more computationally efficient. So that's why an industry cares a lot about efficiency, and they're really where you want to use bioencoders. But just if you want numbers, use cross encoders. The performance is unmatched. So how do we adapt bioencoders to new domains? One approach which is really common for transformers is called adaptive pre-training. So you pre-train on your target domain. So you take a BERT network, you pre-train it on medical scientific publications, and then you fine-tune on labeled data like MS-MARCO. That's fine to do. But as mentioned, our data sets increase. So what we have for embedding learning are terabytes of data. So if you want to have a good retrieval model on scientific publications, it would be kind of really expensive to pre-train on your scientific publications, medical publications, and then to fine-tune on terabytes of data. So that's really time-consuming and expensive. What we want instead is the opposite. We have this one model which was trained on a lot of data, terabytes of embedding pair data, triplet data, and then we want some unsupervised adaptation on the target domain. So first we tested pre-training on target domain and then fine-tuning using MS-MARCO. So that's kind of doable in terms of compute budget. We tested different approaches, math language modeling, and some simple high-level summary. Does it work? Yes. We also presented TSDE and inverse closed task, which I will also present quick in a minute. Does it work? Also yes. And then there were some other approaches from literature, SimCSE, constructive tension, and condenser. And they did not work in our experiments. So they were weaker than the base model. So it's better not to use them and directly use a BERT network. So math language modeling, I hope you're all familiar with it. You take a text, you remove a word, and you try to predict a word. It's great for domain adaptation. So you learn which words are used in your medical domain. Inverse close task does a similar thing, but kind of in a sentence level. You take a paragraph, you randomly pick one sentence, and then you have the remaining text, and you use this as a pair. So you take this sentence and the remaining of the paragraph, you do it as a pair, and then you train with this multiple negative ranking loss. And you want this paragraph be close to the sentence. So also kind of simple pre-training strategy. PSDE was proposed by my PhD student, which matches closer how we use representation models. So we start with a text with noise, so really similar to MLM. You take a text and you delete words in it. You pass it through the word encoder, and then you do a pooling. So you go to a single vector representing all the knowledge in the text. And then you have a decoder where you try to reconstruct the original text without the noise. So this matches more how representation models are used based on word. And then we tested on a lot of different data sets. And what we found is if you go from source to target, so we first train on the source domain, and then we train on the target domain, it does not work that well. So you cannot take the fine-tuned model from MS Marco and train it on your medical domain. So often the performance drops. But if you do the opposite, you first train on medical papers and then train on MS Marco, performance can increase. But as mentioned, we don't want this. This is like really super expensive with large data sets. What we want to train once on a large data set and then adapt to a specific target domain. And there we proposed this year, end of last year, GPL generated pseudo labels. We also see kind of a nice improvement. So this is the out-of-box performance we have with the model. And then you start to train, and the blue curve shows the performance, how well it works. And the orange one is when you combine it with pre-training, but you don't want this pre-training due to computational expenses. So the GPL works in 3 stages. We have query generation, we have negative mining, and we have pseudo labeling. And what's beautiful, I think for an academic setting, it combines all the things you have heard today: doctor query, cross encoders, file encoders, different loss functions. So I think when you understand the approach, you really understand a big chunk of neural search. So I'm really excited to present it here. So what we saw, DocT5 works amazingly, works really robust out of domain. So we start with DocT5. We take a paragraph from our collection, like about Python as a programming language, and then we ask T5 model to generate different queries. So a user could search for what is Python, and he would be happy with this paragraph, or which programming languages uses indentation, and would also be happy with this paragraph as an answer. So you take all the paragraphs you have in the collection and you generate a lot of queries for it. Then you start with the negative mine. So you ask like which programming language uses indentation. You check your corpus about all Wikipedia paragraphs, and you find like different candidates, like Java as a class-based programming language using ESSIR2022, Dentropy, or whatever you want. And then, as mentioned, we want to denoise the data. So here the cross-encoder plays into roles. And cross-encoder also really strong, really performant out of domain. So you take all the queries and all the documents, you retrieve all the possible negatives from the corpus, and you score them with the cross-encoder. And then you can start to train. So first, do we need cross-encoder? And here's like a real example. So we start from this paragraph: futures contracts are a member of large class of financial assets. And then you have the query generated, what is futures contract? And then you have like different negatives retrieved from your document collection. And the issue with -3 is that it's a false negative. So a futures contract is simply a contract that requires party A to buy a given amount of commodity from party B at a specific price. And with this multiple negative ranking loss, we would say, okay, this is not relevant. So this has a relevance of 0, right? Only this one is considered as relevant. But a student and anyone would say, okay, this is a pretty good answer to my question. So why is it wrong? And with margin MSE loss and the cross encoder, we don't do this binary correct wrong solution, but we use like the graded score from the cross encoder. So we ask the cross encoder what's the relevance between the query and the positive, so that's a 10. And what's the relevance between query and the -3, so that's 8.2. So it's not too bad, it's kind of similar. But other negatives which do not make sense, they're like a really low score of 0, sometimes -10 or so. So yeah, so the cross encoder tells us what is a good answer, what's not so good answer, what's a really bad answer. And then we train our bi-encoder model based on that. Any questions on the idea here? So I'm a big fan of margin MSE loss. It's a great loss function, you should check it out. So I always use it and recommend it. You also start with a triplet. You have your query, you have the positive document, and you have your negative document. You encode it in your dense or sparse vector space. You get the representation for query, positive and negative. Then you compute the dot scores. So what's the dot product between query and positive and query and negative? And then you compute the difference for the score of query and positive and query and negative. And you compare it to the difference of the cross encoder scores. So what you want is that distance between query, positive and negative is the same distance as what your cross encoder says. So you use the more powerful cross encoder to teach how should the vector space look like. So which element should be close in the vector space, which element should be distant in the vector space.
So you're assuming that in this case, you're producing scores in the same range as the original cross encoder?
Nearly. It's not directly in the same range, but the margin. So the margin between positive and -3 would be a 2. So you have a margin 2. But it does not make a difference if the bi-encoder says, okay, it's 10 and 8 or 198. And actually what you see, the bi-encoder creates scores which are higher, around 100. But the margin is the same. So the distance between query, positive and -3 is for the cross encoder 2, and for the bi-encoder it should also be 2. But the magnitude is a bit different. So it's for the bi-encoder 198.
And on which task the cross encoder was trained?
So the cross encoder in our task was also trained on MS Marco. And also the doc5 query was also trained on MS Marco. Again, what we see is a lot better performance than adaptive pre-training. So we go from so out of the box is 45, adaptive pre-training pushes you to 49. If you add this generation procedure labeling is 51. And you can combine it if you have enough compute budget with pre-training, gives you like 52. And what's nice about the approach, you can scale it whatever your compute budget is. So if you train longer with margin MSE, in GPL, the model gets better and better, so it learns better and better the specific domain. Right. So the final part, I will be talking about multilingual models, which is also, I don't know, really cool application. So far, there are no good sparse multilingual models, and I think it's a lot harder to do it for a sparse model. So here are like still dense models that shine. That's nice. So how do you get a multilingual embedding model? So the first thing what people found is to modify slightly the pre-training objective, going from mass language modeling to TLM, translation language modeling. So you take an English sentence or whatever sentence you want, and you take the same sentence in another language, for example, in Portuguese, and then you do some masking in both of these parts, and then you just run MLM. And because the model at some time learns, okay, here I have the original sentence in English, and here I have the sentence in, I don't know, Portuguese, it will learn how to transfer it between the languages. So that's one way how you can align the vector space, align the model across languages. And then there are different approaches how to try and train multilingual approaches. One of the oldest is LASER so that's LASER 1, version 1. Facebook is now at LASER version 3. In version 1, it was before transformers, so they took like a BioSTM network. They have some BPE token embeddings, and they basically trained a BioSTM encoder-decoder architecture for translation. So you give as an input an English sentence, it should translate to Portuguese. And what they use is then pooling at the end of the encoder. So you encode the language, you pool it to a single sentence embedding, and that's where the decoder operates on. Sadly, you cannot control what type of embeddings are learned, so what should be closed in the vector space. And it also works kind of poorly to identify similar sentences or also for retrieval, so this does not really work. Then there was multilingual universal sentence encoder, which uses a multitask setup. So you do train on the data you have on question answer pairs, on duplicate questions, whatever, with like the standard multiple negative ranking loss. And then you add a bridging task where you say, I have the same sentence, translated sentence in English and Portuguese, and you want them to be close in the vector space. And you train it in a multitask setup. So you train on the one side what's relevant, related in the vector space, and also how does it translate to other languages. Then there was LABSE from Google, which does this additive margin to multiple negative ranking loss. They first trained on monolingual data set with mass language modeling, then they trained on translation pairs with translation language model, and then they trained on translation pairs with multiple negative ranking loss. And this gives you a really good model if you want to find translated sentences in vector space or in corpora. An approach I presented 2 years ago is multilingual knowledge distillation. So I had like really good English models, but I didn't have like any other language models. And I wanted to know, okay, how can I take my English models and extend them to other languages? And what you do is you start with your monolingual, usually English model. It takes some parallel data from machine translation. So you have these text pairs, sentence pairs, which have the same meaning in different languages. And you take a student model, a multilingual word, for example, and then you encode the English sentence to a vector space, and then you encode the English and the German sentence with the student to the vector space, and you say, okay, all should map to the same point. So all should map to the point where my teacher says, okay, the teacher says, hello world should be in this space, and then the student should also map hello world to the same point, but also for other languages, German, Chinese, Arabic, whatever, should also point to the same point in the vector space. And then the student model just learns to mimic the teacher model and works for many languages, which is kind of a nice approach because it's really easy. So for example, when OpenAI published the CLIP paper, which was like English sentences and images, you just plug in the English CLIP model in it, you train it on parallel data you have from machine translation, and then you get like after, I don't know, 1 hour of training, like a multilingual CLIP model without the need to collect images and text pairs and to train on your large data set. So it's kind of a nice approach. In terms of performance, it's kind of interesting because you see different qualities. So as mentioned, it depends again on the task. How do you want to use this model? If you use it for STS, semantic textual similarity, we see that knowledge distillation works the best, and LABSE and LASER perform really poorly. If you use it on bytext mining, so I have like all sentences from Wikipedia in English, and I want to find all translated sentences in French in the French Wikipedia to get like text pairs I can use for machine translation, LABSE and LASER works extremely well. So again, there cannot be like one universal model that works well for all use cases, but it often depends on the use case. You want what is the best approach and model and what's the best training strategy to use. Another nice concept is language bias, which is kind of interesting also to think more about it. So what's language bias? Language bias means do we see a separation in the vector spaces based on the language it uses? So for example, in LABSE, we see that all the Russian text, if you encode a lot of Russian sentences, are in this blue on the left. And if you encode the same sentences in English, they are on the right. So just from the vector space, it's kind of easy to separate. And two Russian sentences would be considered more similar and closer in vector space than a sentence in Russian and English, even when they're on semantic level closer. And based on the different models, you can see that some models have a language bias. So LABSE has a really strong language bias, while multilingual use and the knowledge distillation, they don't have a language bias. So in knowledge distillation, we know all three, like the English teacher and the English student and the German student. Embedding should all be mapped to the same point. So there you don't have like a language bias. And this has some interesting downstream applications. And I mean, if we think about bias, we would say it's bad and we don't want it. I think it's not black and white if you want language bias or not. So side effects, if you have a model with language bias, same language results are ranked higher just because of the language. So it does not look at the content, just looks, okay, both results are in Russian, so they are ranked higher. And there might be better hits or answers in other languages. So there might be some answer to your question in another language, and just because it's another language, it's not ranked that well. But there are also side effects if you have a model without language bias. So you have the perfect model, no language bias at all. There's like a really severe issue in it. So if I take a multilingual model, like a Google search, image search, I type in wedding, and I look through all my collections of images. I have like millions of images, billions of images. If I type in wedding, I get like something like this. So the bride, she's a white skin, white dress, the man, black dress, has a tie. So that's like kind of like the Western American, Western European style of wedding. And if I have now a search model without language bias, and I type in the same word in Hindi, does someone speak Hindi here? No one speaks Hindi. I sadly have no idea what it's pronounced, so I rely on Google Translate that this is the Hindi word for wedding. I will get the same result because the Hindi word for wedding and the English word for wedding, it's the same point in the vector space. So if I search in Hindi for wedding, I will also get like this Western style of wedding. But probably if I search in Hindi for wedding, I want to see like some Hindi wedding. Same thing for food. So if I type in like food, I don't know, I see maybe burger. If I type it in Chinese food, do I want to see burger? Maybe not. Maybe some other food. So it does not really respect like language difference, cultural differences. And same thing with if you have a text-only model, if you ask like, who's the president, it will focus on, yeah, president, that's Joe Biden. So we'll just find like Joe Biden. If you ask the same question like in French, who's the president? Because it does not understand anything about language, it still says, yeah, president, that must be Joe Biden. So you get all the results from Joe Biden. Probably if you search in French, who's the president, you want to find like some text and documents about Macron. So it's a really delicate and hard thing if you should train with language bias or not. And especially for search, it's a big issue. So do you want to match on the language? Or do you want to match on the content? How do you balance between these? And this, again, depends on batching. So big topic, SSE, data loading, batching, really strong focus. And you can influence based on the batching if you get a language bias or not. So if you train with batch strategy like this, so you have an Arabic question and the Arabic answer, English question, English answer, the model will get like a strong language bias because it's like a student in a multiple choice test. So you have like some question in English, and then you have multiple answers. And you know, okay, if the question is in English, the only right answer can be in English. So I will just check what's the English answer and will say, okay, I have no idea if the answer is correct or not. So I will just mark this as an answer. Different batching strategy is, they call it XX mono. where you have different batches. So you just have one batch on Hindi, one batch on English, one batch on Arabic. So you cannot do this cheating. So if you have your English question, and there are a lot of options in English, you cannot say, okay, yeah, the only correct answer is in English, but you have to really understand what are the different English answers. And then you get a batch with Hindi, so you have to understand what's the correct answer in Hindi. And the third option is XY, where you mix it. So you have a question in Arabic, an answer in English, and you just happily mix it with each other. And so which strategy should you use if you want to do cross-lingual search? So you type in an English question and you want to find French documents. You want to train with XY batching. So because it's directly here, so you have an English query, a Hindi answer. So it's specifically trained for this. If you want a multilingual model and users come and they ask a German question and the German answers, if they ask a Portuguese question, you want Portuguese result, you should train with XX mono because that's the best performance if you have like German question to German answer, Portuguese question to Portuguese question. So again, it depends on what you want, like what type of model do you want? Do you want a language bias or not? And there's no single answer to this. Okay. That's so much I can say about dense embedding models for today. Are there any questions on multilingual models, out-of-domain performance, batching, loss functions? Yes.
Like for the last phase, should it be better than just separate by language? What is the benefit of if we are going to give the answer in the specific language? Why don't we use like have different maybe search engines or different index for each language?
Different. Yeah, I mean, so of course you could train for every language like an individual model. This usually works better. It depends. On high resource languages works better. So if you have like an English model or if you have like a multilingual model, the English model will work better on English. For low resource languages, it's a bit different. So if you have like some languages, if you do not have so much training data, then it helps to train on high resource languages like English, Spanish, and then it works well also on low resource languages. Another thing is in terms of production. If you have like one model which can speak like 100 languages, you can use it really easily in production. So if you're a big search engine, you can just deploy one model and scale this one model, and that works for like any search query you enter. If you have like 100 different models, you need to maintain 100 different models, you need to scale 100 different models. So it gets a lot more difficult to manage that. The third challenge is mixed content. So if you look into text, it's sometimes really hard to say what language is it. So for example, we had some from Taiwan, some Chinese news articles, which has been also translated to English. So you have like one sentence in Chinese, and then the same sentence in English, and then one sentence in Chinese, and then one sentence in English. So it was really a mix, and the same content was there in Chinese and English. And should you map this to Chinese? Should you map it to English, to some new category? That becomes really difficult at some point to really decide what language is it. And you hope if you have like one model which understands Chinese and English, you can just use this, encode it, and return it to the user as a result. Okay, good question. Yes. I did not look too much into DeepCT. I'm also not an expert on DeepCT. So yeah, I mean, it was kind of one of the first endurance fast implementations, and sometimes it takes few generations. Like dense embedding models, that's like really well known. People have used it for, I don't know, many years. So it really advanced in terms of training. But DeepCT was kind of a new, like the first beta or alpha version of a new type of model. And I think that's mainly the reason why it did not perform that well. And then the next generation was kind of sparser, which also did not perform well. And then we found like new approaches, Blade, Unicoil, and so on, which perform really well out of domain. You have a question?
So this question is related to what Carbon that we discussed a while ago. So when you have the dual encoder representations and you actually then try to put it in a search engine to quantize it and or you organize it in a hierarchical way, like with a hierarchical small world, or with bytes and you quantize it, you lose performance. Right? Do you think it's viable to learn these embeddings with the Hamming distance properties, like so that they can be like hash codes?
Yes, I did not include it in this presentation, but there's a really exciting work from this year on learned binary embeddings.
Yeah.
Where you, instead of learning like the continuous dense vector, you learn like a binary representation. So the output vector is just +1 or -1. And we saw that the performance is really close to continuous vectors. There's some issues in terms of unknown domains. So what we saw in domain on MS Market performs really well. And if you transfer it to other medical applications, you see quite a big drop of performance. But the more recent applications, you see like they match really the performance there. Well, then others decrease the gap to like continuous vectors. And they have the advantage that the vector space is much smaller. So instead of like 32 or 16-bit continuous values, you just have like a single bit per dimension. And also the approximate nearest neighbor becomes much faster. So you can use like the local sensitivity hashing, which is like really efficient, and you don't have this massive overhead of the approximate nearest neighbor, which is, for example, HNSW. So that's really exciting new research direction, how to go to a binary space. And they kind of use like a hybrid approach. So the document vectors are binary space, but the query vectors are in continuous space. And then they do a scoring between a continuous vector and the binary vector. And this, I think, gives a lot of advantage.
It's not based in Hamming distance.
It's you do like a two-stage retrieval. So you first take the continuous query vector, convert it to binary. Then you do like Hamming distance in binary space to retrieve your candidates, like top 1000 candidates. And then you have the re-ranking of the continuous vector and the binary vector with dot product. So it's like a two-stage approach: retrieve and then re-rank.
But then you need specialized index to be processed to use that.
Yeah, you can use like, I don't know, local sensitivity hashing. So you have your binary vector, you hash it, and then you can quite efficiently retrieve on that. This reduces quite a lot the memory requirement. So HNSW, so which is the most popular ANN algorithm, needs a lot of memory. So this becomes really, really expensive. And if you go to binary spaces, you can reduce the deployment cost by 100.
The major drawback of HNSW is the setup time. To add more data.
Yeah. I mean, there are many challenges with ANN. It's like setup time. So creating the index is kind of expensive. The index itself, if you have like a really good index, requires a lot of memory. So if you encode the English Wikipedia with 5 million documents, you need a machine with 150 gigabytes of memory. So this costs like $2,000 on AWS. So just having a search function for Wikipedia, which is tiny. And then there are like more general issues like how do you update the index? So how do you add more documents to it? How do you remove documents? How do you update documents? How do you add some filter? Like I only want to search for documents which are published within the last 6 months, or how do I find products in my e-commerce store which cost less than $100. So there are many unknowns how to create this index, how to make it efficient.
I don't know if it makes sense, but do we also add, instead of only using the text, add some information like some metadata? How would you do this? Like concatenating?
Yeah, we found concatenating works quite well. We're kind of limited in terms of length. So transformer network can only encode up to like 512 word pieces. Also, the longer the document, the runtime and compute cost increases quadratically. So it becomes really expensive. And dense representation models, they kind of are bad on lexical matching. So if you want an e-commerce store to find product that costs less than $100, it's kind of hard to do this in a dense vector space, or to find things that can be shipped today or shipped within 3 days. So there people often use like some hybrid approach or some pre-filtering or post-filtering. So they retrieve many candidates and then they remove all the candidates which are more expensive than $100 and cannot be shipped within a day. Yeah, it's a big open question mark in the index structure on how to do it.
So in the question there.
Is there a question?
See the crossroads between cross encoders and wall encoders, like volume encoders. You think there is explore?
Yeah, so at the end, I mean, so polyencoders, they encode the documents into, instead of creating like single vector, dense vectors, they create multiple vectors, and they do some attention based on query and these multiple document vectors. At the end, it's always a trade-off like accuracy, performance, and memory. And you can trade it. So if you say, I do not care about memory, you can create something like covert, where you get for every token in your document a continuous vector. But this creates like an index which is super big. So if you encode Wikipedia, you need like terabytes of memory, which makes it again really expensive. And then you can trade it on like how much am I willing to spend on compute, how much am I willing on memory at this, and how much do I want to sacrifice on performance. And so at the end, that's a trade-off. Where do you want it to be? What's really expensive for you in deployment? Is memory more expensive? Compute time more expensive? Performance more expensive? So I would not say there's like a single best solution. That's like Pareto curve in a 3-dimensional space. So memory, compute cost, and performance. And then there are like different points in this 3-dimensional sphere where you can optimize. But yeah, sadly, a lot of researchers just focus on performance, or they do it on like 2D, say, okay, this is the performance and inference, like latency, but have not seen so far like some work in the 3-dimensional space, like memory, compute cost, and performance.
Well, any other questions? Okay, let's thank the speaker then.